And I'm going to show the work named Calibrated Digital Predistortion using a vector network analyzer as the receiver. So this presentation is organized as follows. First, I will give a brief introduction about the most common testbed used to obtain the static and dynamic behavior of a PA. The context, motivation, and challenge will be discussed. Then I will talk about how we can transform a vector network analyzer into a vector signal analyzer. A verification using DPD linearization will be discussed, and then some conclusion will be given. So first, the characterization of a PA for continuous wave signal is usually performed using a vector network analyzer. The dynamic behavior of a PA is usually acquired using a vector signal generator for the modulated RF source and a vector signal analyzer as a receiver. We can see here a testbed to obtain a dynamic behavior. And in this paper, we investigate the alternate use of a vector network analyzer to perform the function of a vector signal analyzer for the acquisition of LTE and OFDM waveforms, so as to facilitate both the PA behavioral modeling and DPD linearization of an amplifier. Okay, so basically we have three motivations for using the vector analyzer as a vector signal analyzer. The new one, the first one is the new approach benefits from the large dynamic range of the VNA and the availability of the spectrum analyzer software option for the acquisition of the Fourier amplitudes and phases of periodic modulated signal. The second one is the allowance to use the same VNA and calibrated testbed for both the continuous wave nonlinear response and the modulated vectoral response of a device without breaking contact. And the last one, but at least, the possibility of measuring 5 channels in the PNX at the same time using the spectrum analyzer option suitable to obtain the lookup table for outphasing PA. So some challenge that we have in this testbed is that we need to develop a phase calibration for the spectrum analyzer receiver option of the PNX to operate as the vector signal analyzer. We need to perform a time alignment between the receiver and the transmitter, and we verify the new approach using DPD. So we arrive to the best part, how we transform the vector network analyzer into a VSA. For that purpose, I will discuss about the testbed use, the measurement procedure, and the most important, the phase calibration developed for this work. For this purpose, we use modulated RF signal, we use LTE and OFDM using 64 QAM modulation with a bandwidth of 5 megahertz and a spacing tone of 1 kilohertz, so that gives us a number of tons of 5,000 tons and a sampling frequency of 40 megahertz. So this is the testbed used in our lab. It's very simple. We just use the vector signal generator to generate the modulated signal and the vector network analyzer using the spectrum analyzer option. We share the 10 megahertz between the VSG and the vector network analyzer to lock the LO. And for the measurements, we are going to use the CFL2500PA. It's a commercial power amplifier for mini circuit that has a gain of 28 dB and output power of 16 dBm at P1 dB, and everything is controlled remotely for our PC using Ethernet connection. So let's talk about the measurement flow chart. So first of all, we need to calibrate the system in order to get the waveforms at the reference plane of the duct. So for that, we use, as we know, the short open load and unknown through. And we also do a power calibration to remove all the losses of the RF path. The second step is generate the modulated signal. We generate it in MATLAB, and we download using Ethernet connection to the BSG, and then we need to configure the spectrum analyzer option in our PNX. So for the configuration, we use a center frequency of 2.3 gigahertz, a span of 20 megahertz, and the spacing tone is 1 kilohertz, so that means that our signal has a periodic of 1 millisecond, and the vector averaging is put to 20 to improve the dynamic range of our receiver. So then we store the data in MATLAB. We need to do a phase calibration that we are going to discuss right now. And the last step is the post-processing of the data. So this is the receiver signal, the 64 QAM signal received using the option of the spectrum analyzer. As you can see, we can see the constellation. So the first step that we need to do is an oversampling, and it's due to the fact that the original signal has 40,000 samples, and the receiver signal has 20,000 samples. We do using a zero padding in frequency domain, and then we need to do a synchronization in time domain between the receiver signal and the original signal. To extract the phase, we use a non-OFDM signal with a bandwidth of 20 megahertz and a spacing tone of 1 kilohertz. So that gives us 20,000 tones, and we use a sampling frequency of 40 megahertz. We use the receiver R2 to extract the phase calibration, but also we see that all the receiver has similar behavior in terms of the phase. This is the equation that we use to extract the phase calibration. It's very simple. It's just the difference between the phase of the raw data and the original data, plus the delay difference and the phase offset. So in the figure, we can see the behavior of the phase correction. We did like 11 measurements using different 20 megahertz OFDM, and we can see the behavior is similar. And the average standard deviation over the 20,000 ton was 0.42 degrees, with the maximum standard deviation of 3.7 degrees. So we are in position now to begin with our post-processing of the signal. First, the oversampling in frequency domain. Then we apply the phase correction that we observed before. We transform the signal to the time domain. We do a synchronization in time domain. It's kind of slowly, sorry. So we can observe in the constellation that the dots are still rotated, so that indicates that we need another fine-tuning synchronization. This is done computed the phase offset, and it's doing using least mean square, and we apply the phase correction as we can see in the equation that is at number 2, but it doesn't appear there. And to finalize, we do a fine-tune amplitude calibration. So we can see here the constellation in the different steps of the post-processing. The first one is the constellation acquired. The second one is the constellation before the fine-tuning. Okay, here we can see the phase offset, and then we correct the phase offset, and we get this constellation with an EVM of 1.96%, sorry, and then we apply the amplitude calibration, and we improve the EVM. We have just 1.48%. Okay, so now we need to verify our BSA. So we do that linearizing the ZFL2500 amplifier. This one was linearized by Predistortion the input signal XN using the technique of indirect learning. The input XN were modeled in terms of the output data Y using generalized memory gain function with a memory depth equal to 3. The memory gain function are implemented using a cubic spline lines with 25 segments, so that gives us a total of 78 coefficients. Okay, so let's see some results for the LTE signal. We can see first that the PAPR of the input signal and the output is almost the same. Also, the NMSE after the predistortion is pretty good. And the adjacent channel leakage ratio improvement of about 29 dB. Oops. No? Okay. So this is the AM to AM and the AM to PM of the PA before and after the DPD. The black, where is the black? Okay. The black is before the DPD. The blue one is the inverse of the PA using the equation explained before, and the red one is after the DPD. We can see in the spectra that we improve very good. We have a 65 dBc of adjacent channel power radio. We also apply the same using an OFDM signal of 5 MHz, calibrated with the 20 MHz OFDM. We can observe, for example, after the DPD, that we can recover the constellation. It's important to say that for the input and output, we apply the same phase calibration and the same procedure described before. So some results of the OFDM signal is the same. We get almost the same PAPR. We improve the adjacent channel leakage radio. The output EVM after the DPD is better than the input, as you can see in the table, due to the fact that the dynamic range of the output receiver is higher than the input. And allow me to introduce some preliminary results that weren't reported in this paper. And it's the DPD linearization of dual input outphasing PAs using the vector network analyzer as a vector signal analyzer. For this purpose, we use a dual input CICESE Doherty TPA working in mixed mode, where the main PA is working in class B and the auxiliary PA is working in class C. This is our test bed. So they are time alignment. Okay. So some results using the continuous wave characterization. We get the gain versus the output and the efficiency, the drain efficiency. And this is obtained using the swapping the two input powers and the phase difference between the inputs. So then we get the lookup table to high efficiency or to get the linear gain. We apply to the modulated signal, and we can see here the red one is the AM to AM with modulated signal, and the black dots is our lookup table. We can observe that the modulated signal follow the behavior of the continuous wave. We can observe the constellation after applying the lookup table at the output of this PA. The AM to AM before and after DPD. The blue one is after the lookup table, and the red one is after the DPD. We can observe that we get the 54 dBc adjacent channel power radio after the DPD, and the constellation at the output was recovered. So the OFDM signal used for this case has a 9.53 dB PAPR, and we use a 2.5 MHz bandwidth. The reason is that this new option, the spectrum analyzer, is just have a bandwidth of 30 MHz, and this PA have a very high, a stronger nonlinearity. So we reduce the bandwidth of the signal. The PAPR is almost the same after the DPD. The NMSE was very good, -39, and the EVM acquired was just 1%. So some conclusion, a new testbed using a vector network analyzer with a calibrated BSG to characterize the nonlinearity of device using modulated waveform on the realistic large signal operation was presented. In order to recover the modulated waveform in the time domain, a phase calibration in the frequency domain was developed to compensate to the IF filter response and group delay of the VNA receiver and testbed respectively. The phase calibration was extracted using a 5 MHz OFDM signal with 20 MHz bandwidth and modulated using 64 QAM. The consistency of the calibration and modulated waveform recovered in the time domain and verified by the successful behavioral modeling and digital predistortion of the PA, and as demonstrated in the talk A1 by Dr. Jan Perspeck, the spectrum analyzer option already supported EVM measurements with gigahertz bandwidth, so we will hope to be able to extend the capability to out-of-band distortion measurements. So that's all for me. See if you have any question.
We have time for some questions.
Yes, I have a question on, it seems that you get in some cases a better EVM at the output of the power amplifier, of the linearized power amplifier, than you have at the input of the amplifier.
I did get the question.
Is it okay that you get a better EVM at the output of the amplifier, of the
Yes.
linearized amplifier, than you get at the input? It is better?
In this case, for example, that I
Yes.
get better EVM after the DPD at the output compared with the input. The reason is that the dynamic range of the output receiver is higher than the input receiver, so that's why we get a better EVM. You can see here. So the yellow is the input PA. You see the floor noise, and the blue one is the output. You see that the floor noise is less than the yellow. So that's the reason that we have a better EVM at the output. The dynamic range is better at the output receiver than the input.
Okay, thank you.
You're welcome.
Any other questions? If not, let's thank the speaker again.